Thank you very much, Yanai. So I'm thrilled to present this work on dynamic stochastic matching, and this is joint work with Ömer Saritaç, who is a PhD student at the London Business School. So the broad motivation for this work is that not only matching platforms have to think about the quality of their matching decisions, but they also have to think quite crucially about the timing of these decisions. And the reason is that matching markets are often dynamic. There are new agents that constantly enter these markets who are more or less willing to wait. Who are more or less patient. And in case they're not matched on time, they simply abandon the market. So as a matchmaker, you have to balance this limited patience with another fundamental challenge of matching markets, which is the sparsity of the demand. So if I want to take a concrete example, in the sharing economy, suppose you're, say, running a carpooling platform. You want to pool riders based on their origins and destinations, such as Uber or Lyft or Didi. So even at the busy time, in a large urban area such as New York, as you can see on this heat map, the demand can be quite sparse based on these origins and destinations. In fact, for the vast majority of origins destinations, there might be less than one request per minute, which essentially means that carpooling is hopeless unless you are making the users of your platform wait for a couple of minutes at least. And indeed, the vast majority of ride-sharing platforms do leverage the willingness to wait of their users to improve the efficiency of their decisions. So the goal of this work is to think about a principled algorithmic approach backed by performance guarantees to strike a good trade-off between the risk of abandonment and the efficiency or the thickness of the market on the other hand. And the algorithm will be able to leverage not only the network structure of the economy, but also what is known about the arrival patterns and as well as the abandonment pattern. And this is a fundamental gap in the literature on online matching that we're addressing. So I'd like to jump in directly to the model that we call dynamic stochastic matching, and tries to kind of capture all the features I've highlighted in this example. So we're facing a networked economy, which is represented by an edge-weighted graph. So here, each node or vertex in this graph corresponds to an agent type. And the cost along an edge represents the quality of the match between agents of different types. So the platform's problem is essentially to solve a stochastic control problem, a Markov decision process. So it sees a stream of arriving agents of different types, so that the arriving rate is lambda I, and each of these agents has an exponentially distributed willingness to wait, to stay in the system. So the abandonment rate is denoted by mu I. And within that time span, the platform can match agent I with anyone he's compatible with. And in case the agent abandons the market, we incur a cost, an abandonment cost. So the long-term goal is to minimize the expected average cost. Or if you're thinking about rewards instead of cost, the goal is to maximize the long-term average rewards. So obviously, if you were able to solve this Markov decision process optimally, the cost minimization or reward maximization would be equivalent. But this is a high-dimensional dynamic program that is intractable. So we will resort instead to some sort of approximation algorithms. And as a result, the cost minimization and reward maximization problems will be fundamentally distinct. So the remainder of the talk, we will go from this modeling approach that I would think is quite general, can capture stochastic arrivals and abandonments at the same time, and go from that to design matching algorithms that are efficient, that can be computed in polynomial time and have strong theoretical guarantees. And I think the interesting insight here is that because of this, in order to account carefully for arrivals and abandonments, the flavor of these matching algorithms will be quite distinct from standard matching algorithm. That's these noteworthy properties I will try to highlight in this talk. So we'll resort also to some technical ideas that might be of independent interest, such as benchmarks, value function approximation, and simulation-based techniques. And lastly, I will touch on how this feeds into practice. So we have conducted a numerical exercise through which we show the value added of carefully accounting for arrivals and abandonments within your algorithm design. So obviously there's been a very wide spectrum of literature on matching in general that is related to our work, and I'm simply mentioning here a few highlights, a few papers. So there's a long-standing literature in computer science and operations research that focuses on rigorous analysis of online matching algorithms. And you can think about these papers, this line of work, as focusing on an extreme kind or extreme type of arrivals and abandonments, where you have online customers and offline resources. So the online customers have to be satisfied and served immediately, so they're infinitely impatient, whereas the resources stay throughout, so they're infinitely patient. And our model tries to capture an in-between and a kind of more nuanced view on the timing. And as a result of that, our model also is reminiscent of matching queues and the control of matching queues. So there's also quite a lot of work in that area. I'd like just to mention that one takeaway, one morals from this line of work is that even if you fix a simple policy, a simple matching policy, it is actually quite difficult and intractable to characterize the steady state distribution that is induced by that policy. So in other words, by looking at analyzing our problem in steady state, we're not really making things easy for us from a purely analytical perspective. And lastly, this is not the first piece of work on dynamic matching. There's a number of excellent papers in the very recent years on this. I would like to mention that the kind of departure here is that we're focusing on a slightly less stylized model where arrivals and abandonments are fully stochastic. And this has important implication in terms of algorithm design. So to our knowledge, this is the first paper that proposes algorithmic means by which you can actually leverage prior knowledge about the arrivals and the abandonments of the agents in the market to achieve better performance. And in fact, as a teaser, I'd like to start by kind of answering a natural question. Do we really need novel algorithms to solve this family of online matching problems? So what about existing algorithms? And in fact, there's a family of policies or algorithms that are widely used in practice, which are referred to as batching policies. So these are policies that compute maximum and optimal matching at the periodically. So after t units of time, where t is the batch window, which is a parameter of these algorithms, the platform will optimally match all the agents that have accumulated in the system and proceed to the next batching window. So what we show is that, in fact, the performance guarantee of these algorithms, this family of batching policies, could be arbitrarily bad, even if the batching window is optimally tuned in that particular instance. So we have quite a strong negative result on the performance of this family of policies. And the intuition here is that it is not possible through a single batch window to synchronize the agents of different types. So in other words, as long as there's a slight imbalance between the arrival rates, the frequency of arrivals, or the abandonment rates of agents of different types, it's not possible to put them on the similar time clock if you want to balance the abandonment cost with the quality and the efficiency of the matches. And as a result, we need a more granular algorithm to do that. And this is where our main results come into play. So we develop approximation algorithms that achieve constant factor performance guarantees with respect to the optimal solution of the Markov decision process. So I'll first state our result in the cost minimization setting. And because cost minimization problems are often harder, we'll add a little bit of structure to the problem. We'll assume that the costs satisfy the triangle inequality, and this sort of metric property is motivated by applications that in economy networks that are spatial, such as ride-sharing networks, for example. So what we get is a factor 3 approximation for this problem. And while I won't go into the details, I just would like to mention the flavor of the policy. So we call it vertex additive. The idea is to look at each vertex in isolation and try to quantify what is the marginal cost that this particular type of vertices incurs for the system. And this is computed via a simplified version of the problem where we overlook some of the network effects. And then with this knowledge of this notion of marginal cost, we we go back to the Bellman equation of the dynamic program, and we construct an approximation of the value function that is additive, that linearly adds up these marginal costs. And we show that this approach is sufficient for our purposes in order to obtain a constant factor approximation. And our second and our main result is to develop a constant factor approximation in the reward maximization setting. And this result doesn't hinge on any additional assumption on the network structure or the abandonment patterns. So we get a 1/2 1 minus 1 over E approximation for the problem. And I'll try to touch on some elements, ingredients of our approach, as well as the algorithm. So obviously, given the complexity of this Markov decision process, we first need to use take a simpler view on the problem and have a good benchmark at hand, not both from a design perspective, but also from an analysis perspective. And as in many other papers in this literature, we resort to a linear programming approach. Oftentimes, these linear programs come from a certain scaling of the system. Like you can interpret them as a fluid scale or a large market regime scale for the problem. But if you think about the abandonment structure or the fundamental reason why this problem is hard, this completely vanishes if you take any sort of scaling of the system. So as a result, there are some differences here that I would like to mention. So the key idea is to distinguish between something we call passive and active vertices. So passive vertices are vertices that are matched with those that arrive earlier, and active vertices are any other vertex. This is for a fixed policy. So in other words, active vertices are the ones that are waiting in the system, and we'll have a decision variable xij that captures the match rate of active type I vertices with passive type j vertices, and we'll plug this decision variable within a linear programming formulation. So the average cost can be expressed linearly with respect to these variables. There's a flow balance equation, as one might expect, but then the extra interesting ingredient here is to have a number of constraints that place a fundamental limit on the amount of abandonments in the system, that lower bound the necessary amount of abandonment incurred in the system as a function of these decision variables. And it turns out that this is a critical piece for us to be able to capture the effect of abandonments in the system. So armed with this knowledge, I'd like just to mention that the optimal value of this linear program is generally incomparable to what we call the offline optimal solution. So if you know exactly the sequence of arrivals and abandonments, you might be doing much better than this linear program, which means that basically the best possible competitive ratio for this problem is of 0. So armed with this linear programming benchmark, we develop a simulation-based algorithm that we call randomized compatibility. So the idea is, in the first step, to use a modified version of this benchmark, but it essentially has the same structure, to get a flow vector that represents the match rates in steady state. And as you might expect, the second step would be to try to simulate the resulting flow vector using a randomization strategy that tries to mimic the proportionality of assignments in the system. But here, there's again another interesting tweak that arises due to the abandonment, the trade-off between abandonment and matching efficiency, which is that it is very difficult it's not possible actually in general to use a randomization strategy that will thin out the Poisson arrival process. Because if you're thinning out the Poisson arrival process, you're also increasing the amount of weighting for agents in the system. So you should be very careful in the way you design this randomization strategy in such a way that you can benefit from pooling. So pooling means that for a given agent, I can decide to match him with a subset of other types in such a way that I can minimize the amount of time he spends in the system and the level of abandonment that he incurs. So how do we do that? Well, we will first, again, using the flow vector, assign a random label to each vertex as being active or passive. And then the thinning out of the Poisson, of the stream of arrivals will only happen for the active vertices, the ones that are waiting. and we won't be doing a similar thinning out for passive vertices. So we'll have to keep the pooling effect. And we capture this pooling effect by creating the composition of the flow vector into what we call compatibility sets that are subsets of types such that the active vertex will be matched greedily to any vertex that arrive first within that group. So we want to capture the synergies within a pool of arrivals of types. And it turns out that our constraints of the linear program are exactly typed for this particular structure that we are creating. Lastly, in our analysis, we still need to argue that this is a sound approach. And as I said earlier, it is intractable to characterize a stationary distribution, even if you fix any policy. So instead, we resort to a new novel proxy that we call the virtual Markov chain, which is an approximation for the stochastic system. So I'd like to end by mentioning how this feeds into practice, and as we simulated these policies, what did we observe? So I'm showing here simulations were conducted with the New York taxi data demand, and where we're comparing different algorithms, including batching and vertex additive. There are two metrics of interest given the trade-off that we're trying to resolve. So one metric is the saving rate, which is essentially by pooling riders, how much cost are you saving? This is an indicator of matching quality. And then the other metrics we care about, obviously, is the match rate, which is what is the proportion of the agents that you're successfully able to match and that don't abandon the system. And what we observe is that, in fact, not only there's a trade-off between these two dimensions, but as long as the platform seeks a very high match rate, there's very limited headroom, and the algorithms are actually quite similar in terms of performance. But as the platform gets more interested in matching quality, the performance gap between the vertex additive policy and batching policy can increase quite widely. So this is a good indication that there is value added in accounting for arrivals and abandonments. So why is that? Let's dig a little bit deeper into the data. The fundamental reason is that not all agents should be exposed to the same amount of weighting. So waiting time should be proportional to their relative arrival rates and abandonment rates for these particular types. And here I'm decomposing the amount of weighting as a function of trip length, which oftentimes correlates with like sparser areas are where the trips tend to be the longest. So what we see is that our algorithms are able to modulate the amount of weighting as a function of the type of agents we have in the system, whereas the batching algorithm applies a uniform amount of weighting for everyone and is not able to capture this element of differentiation. So I'd like to conclude here by summarizing our results and mentioning some interesting open questions. So our first observation is that there is definitely an important punchline in this work is that there is value in designing matching algorithms that can be calibrated to the agent's arrival and abandonment patterns. So we can leverage that information to get better algorithms. There might be interest in using our solution concept, the constant factor approximation in steady state for other online matching problems. And lastly, there are a couple of open theory questions that I've listed here that might be of interest that directly stem from our work. And with that said, thank you all very much for your attention, and I'm happy to take questions.